Carmen is going to be helping me keep everyone kind of muted. Again, just as a reminder, please keep yourself on mute, but please feel free to throw questions on the in the chat as they come up. You go to the next one, please, Carmen. Oh, might be going. There we go. As everybody knows, Puget Sound ASHRAE is a volunteer organization. We are always looking for more assistance and more help. If you have any free time, if you can spare, you know, an hour or two a month, we would always love that. Please feel free to reach out to any of us on the board or myself after the meeting. We'd love to chat and see what is available for you. Here's some of the open chairs that we have, but again, anytime I'm sure we can fit you in somewhere. If this is not, if any of these are not specific to what you're looking to do, we can always use the help. Upcoming events, we've got in March, we've got a discussion on the upcoming Washington State Energy Code. And then in April, we're looking at talking into some of the smart building solutions and connected buildings. And then in June, we are doing our annual golf field day at Harbor Point, and would love to see everybody there, and more info will be coming out in the coming weeks on these events as well. So today's presentation is going to be acoustical considerations for building design by Chris Diezik. I'm sure I butchered that, even though I just had him kind of coach me through that as well. He's the general manager of noise control for Price Industries. He has a BS in mechanical engineering from the University of Manitoba. He has put 15+ years in HVAC acoustics and noise control. So we're very excited to have him join us and help teach us about acoustical considerations. Chris, we'll kind of leave that off to you. So if you want to do any intros on the presentation, the floor is yours.
Sounds good, Ty. Thanks for the intro. Let me just share my screen here. Bear with me. There we go. All right, sorry about that. My presenter mode wasn't popping up properly, but I think we should be good now. Can someone just confirm they can hear me and see my screen okay?
We're good to go.
Awesome. Okay, thanks guys, sorry about that. So my name's Chris Diezik, as Ty had mentioned, and I'm pleased to be here today. I love supporting ASHRAE events and ASHRAE chapter meetings, and wish we could be doing this in person, but virtual will work as well. And I'm going to talk to you guys today about acoustical considerations for building design. And in general, acoustics and sound are something that's extremely important with commercial buildings, but often either forgotten or sort of mistakenly assumed it would be okay. And I hope today's presentation is informative on some of the background considerations that should really be looked at and made when working on projects. Again, a quick introduction of myself. I'm a professional engineer with a mechanical background in HVAC, and I've always been involved with acoustics and noise control in my career with Price Industries. Been here since 2007 and primarily focused on commercial building noise mitigation and solutions around problems that occur. So today's presentation is going to have a couple of points that I'm going to review with you guys, starting with talking about the importance of acoustics and sound, and then delving into the three main aspects that we look at with respect to acoustic analysis and understanding what the guidelines should be for any sort of commercial building space. And then finally, I'm going to touch on and introduce some quiet HVAC systems that may be a little bit newer or different from the traditional sense that you're familiar with today. So let's begin with the importance of acoustics and sound in general. And some of this might be a little bit fundamental for what you're used to, but I think it's a good refresher and sets really the framework for today's topic. This slide has two quotes that I've come across over the years, and it really speaks to the importance of sound One is that patients complain about noise 2 times more often than anything else in a hospital, including the food. And in hospital and healthcare applications, sound can be a real problem, preventing communication or people being able to rest and relax and recover. And it's something that can be controlled and designed better than maybe it is today in certain circumstances. The second quote is that guest reviews of over 5,000 hotels had found that noise gained more negative mentions than really any other complaint. And noise is something people like to complain about. It's disturbing, it's distracting, it's annoying, and it gives people a reason to maybe give a hotel or a business a lower rating or recommendation than another space that would be more pleasing and acceptable to be located in. When we talk of commercial buildings, we often look at the spaces and how they're used and speak to the acoustic environment of these spaces. What I mean by acoustic environment is the over and underlying acoustical background, the background noise within a space, as well as the materials that are used to construct the space, whether it's a hard reflecting surface or a very plush sound absorbing surface. Spaces can sound and react very differently. Most commonly, when we look at commercial buildings, we use terminology like dead or live to refer to the acoustics of a space. These sound a bit morbid maybe and not the most pleasing type of spaces, but this really is a way to dictate the acoustical reflectiveness of a space, how absorptive or reverberant a space would be, and how sound within a space would propagate around it. Usually most spaces are more absorptive than less. Because of things like commercial carpeting or acoustical ceiling tiles, sound isn't going to be allowed to be reverberated as easily when these are present. Jumping into some of the relevant terminology, these are also important to understand and might be, again, a refresher for some of you guys. When we speak of noise, in its simplest sense, really we're referring to any unwanted or distracting or disturbing sound. And there's many different examples and types of noise, obviously, in fans outside cheering for maybe an opposing team, or even like a hand dryer in a bathroom type space. Noise can be anything that's either excessive or unwanted. In most traditional examples, it's equipment or devices that are producing excessive amounts of noise, like fans or pumps or chillers and things like that. When we describe sound in general, there's 2 main ways that we often refer to sound. And there's discrepancies and confusion around this, I find. And I thought I'd take a minute to provide a bit of an analogy that makes it easy to understand and remember moving forward. When we describe sound, we often use the terminology sound power, which is denoted LW. And what sound power is typically referring to is the amount of acoustical energy that a source would radiate independent to the environment. This is commonly measured in watts, and the big thing to take away with sound power is that it's independent of environment. It doesn't really matter where it's located. Sound pressure, on the other hand, often denoted LP, refers to a pressure fluctuation of sound that is more dependent on environment and depends on things like the acoustical environment, the space, the distance, in how it's perceived. And sound pressure is often measured in pascals. And we use sound pressure to refer to things like the design criteria, the amount of NC or dBA within a space or within a specific area. An analogy I like to use for these terminology is looking at the heat from a fire, and everyone's felt or seen or been around a fire, and thinking of the heat from a fire to be analogous to that of the sound from a source, you can look at it similarly in that the larger the fire, the bigger the fire, the more logs, the more wood that's burning, the more power or energy that fire has. Similar to sound and sound power, the bigger the source, the more energy that source has, the louder it's going to be. As you move away from that fire, the intensity typically lessens. The closer you get, the more heat you're going to feel. The pressure can be seen as dependent on the environment, dependent on your distance, and that would be the heat that you feel from that power of the fire. Sound power, sound pressure can be seen quite similarly, and I hope that's a good analogy that maybe gives you a better understanding of the differences between power and pressure. Sound is quite interesting in that you can't see it, and it's often misconstrued or confusing for people to understand, where is this noise coming from and how is it being transmitted. And in general, as sound moves from the source to a distance, the energy that's present will dissipate. The further you are away, the less intense that energy and sound would be. And there's different rules and inverse square laws for sound that for each doubling of distance, your area is essentially lessened by a quarter. And this image here shows that, in that as you move further away from a source, that intensity now lessens over that same distance. We often refer to sound and sound measurements taken in a free field. A free field could be something like this here, where it's actually seen as propagating in all directions equally without any sort of reflection or refraction. But it could also be something like this, where sound is maybe measured or being presented in something like an anechoic chamber, where there's not a lot of reflection or reverberance present, and it can travel easily and freely in a specific direction. Another thing with sound and sound transmission is looking at sources of sound and how sound transmits from a source. When we look at a line source, we often look at multiple sources that would reinforce each other. Something like this here, where there's multiple rooftop units and they're added in series along that certain length or span. And the more sound sources that might be present, the more sound energy could transmit outwards from it. Another graph to look at the difference between a point source, an individual point source, and a line source is something like this here, where noise reduction would be seen differently compared to a line to that of a point. As you move further away, the noise reduction of a point source is actually higher, in that it's not reinforcing individual point sources. There's only a single point, a single source, whereas multiples will help propagate that sound maybe further with less of a reduction. Another table I like sharing with people that is often not really seen in your daily working environment is that humans in general have a very wide range of hearing. We, on our best days, can hear between maybe 20 hertz and 20,000 hertz. Most adults, as they age, their hearing range is going to decrease as they're exposed to loud sound for extended periods of time, or they attend sporting events or rock concerts or whatever might damage hearing. But in general, humans have a very wide range of hearing in frequency. Human speech is a narrower range of frequency, about 125 to 8,000, depending on the individual, depending on the audible nature of their voice. But some animals have very wide ranges of hearing outside of what we can hear. Animals like elephants, for example, have an extremely low range of hearing, whereas things like mice or bats can hear extremely high frequency ranges. Politicians, well, we're not really sure if they hear anything, so we'll kind of exclude them for this purpose today. When we speak of hearing ranges and frequency ranges, we often look at wavelength with respect to frequency. Wavelength being how much or how long the wave of sound would be with respect to a certain hertz or octave band. And it's a simple formula in that the wavelength can be calculated by the speed of sound divided by the frequency. So in this case, if you look at the table, you can see that a 63 hertz frequency range would have a very long wavelength, 18-foot wavelength. Whereas you move into a higher frequency range, 4,000 or even 8,000 hertz, these are very short wavelengths, 3.4 inches or 1.7 inches. High frequency, short wavelength. Low frequency, long wavelength. And what this sort of means is that depending on the frequency range of a sound, it's going to sound quite drastically different. A low frequency dominant sound is going to sound like a rumble, whereas a high frequency source or noise would sound more like a hiss. And depending on the source of the noise and what's being produced and audibly heard, it can be more disruptive than not. In general, humans are more distracted and disturbed by higher frequencies, in that a hiss-sounding noise for an extended period of time would be considered quite annoying or obtrusive, whereas a rumble type noise maybe isn't acceptable, but it's less annoying, less of a complaint. Again, on some of the fundamental terminology, when we refer to noise and sound, we often use things like this table here, which is actually referenced out of the ASHRAE Applications Handbook. We speak of things like NC or RC or dBA, and these are single number references and easy ways to refer to the sound pressure within a space. Again, sound pressure independent or dependent of environment. Something like an office or a boardroom or a conference room would have a specific noise criteria or NC associated with it. If you're not familiar with these ratings, they're quite simple to understand, and I'll take a minute to kind of describe what it is. In general, these single number references, NC, RC, dBA, are taking that individual octave band sound pressure level, and if you look at the table at the top, in 8 different frequencies, octave bands, you have a corresponding sound pressure, 49, 42, 40, and so on. If you take those sound pressures and you plot them on a standardized set of curves, this is how you typically obtain those single number references, like the NC, for example. NC, or noise criteria, which is really the most common one that we see being used, takes those 8 octave bands, and if you look at the red line on the curve, once you plot them, the highest point and curve that is then crossed would set your noise criteria. In this case, it looks like about 2000 hertz would yield roughly NC 40 criteria, whereas that would be the highest point on that curve, and now your 2000 hertz octave band would be setting your NC 40 criteria for this example. NC was developed in the mid-1950s, and it's often used for either referring to the background sound within a space or using for rating products like terminals or diffusers, or even diagnosing maybe if a space is acceptable or not. It is a little bit limiting in that all you get really is that single number reference, the NC value. You're not really obtaining much information on the spectrum of sound, or if there's a dominant frequency that's maybe causing that spectrum. RC is another type of criteria that's primarily used for referring to indoor spaces and what the sound level in that space would be. Used as both a design tool or a diagnostic tool, it's similar to NC in that you would plot your representative sound pressure levels, and then through some averaging, take a look and understand if there is some indication of the spectrum of sound, whether it's a rumble, a neutral sounding spectrum, or a hiss. Again, like I mentioned earlier, low frequency dominant, mid frequency range, or high frequency. And you can see on the curves here and the color coding, whether it's a rumble, a hiss, or a neutral sounding spectrum, can be very beneficial. With sound, you're most likely familiar with the decibel scale as well. We use this a lot to refer to acoustics and noise, whereas on the low end, things that are very quiet, 10, 20, 30 decibels. As you get into the middle range, 40, 50, 60, these are where primarily we operate and have most indoor spaces. And as you get into the higher decibel ranges, these are extremely loud semi-industrial applications that you need to be sensitive to your hearing. Wearing hearing protection if you're exposed to high levels of sound for any extended period of time is highly recommended, as to not damage your hearing and have any sort of long-term effects, which can cause a lot of health problems apart from the audible degrading of your own hearing. Sound in general is looked at and described when we look at different types of mechanical devices, like this here, where there's 2 different sources operating at the same sound power level. Again, sound power, LW, independent of environment. If we had 2 fans, both running at 80 decibels each in the same space, you would take these and add them together, right? 80 plus 80, 160 decibels. Very, very loud. Well, thankfully, that's not the case. When you add sound, they're added logarithmically together. 80 plus 80 is 83, and the mathematics behind that is essentially a base 10 log added together to yield that 83 decibel total. A simple and kind of a handy graph to show this is that when two sources are of equal sound level or sound power, the difference between the two sources is 0, you effectively add 3 to the louder of the two. And in this case, the example we had was 80 and 80. They're the same, 0 difference between. You would add 3 to get 83. As sound sources get further away from each other, due to the nature of the logarithmic scale, the amount that's added reduces quite quickly. In that, if you had a 4 decibel difference between two sources, you would now only add 1.5 decibels to the two sources. So an example could be 80 plus 76 would actually only yield 81.5. And as they get further apart, if you have two sources that are 10 decibels or more apart from each other, the secondary, less loud source would effectively be negligible. 80 plus 70, for example, would actually just be 80.4, almost rounded to 80 decibels. So it's something that I feel is important to understand. And really, when you're familiar with some of these basic concepts, it makes understanding and diagnosing sound in commercial buildings a lot easier. The next topic I wanted to introduce is around what we call the 3 main aspects. And what I mean by that is that there's 3 main things that should be looked at and considered with respect to sound. This image here is a little bit busy and messy, but let me break it down into its elements. In general, the 3 main aspects I wanted to speak of are the source, the path, and the receiver. And in general, any sound application or noise problem can be broken down into these elements. I may be overly simplifying it a little bit for today's presentation, but in general, there's a source of noise, a path in which that noise will be transmitted, and then finally the receiver of that noise. Again, there's many different types of examples and things that can be potentially complicated when looking at it in this scenario. Sources can be a variety of things. They can be mechanical equipment. They can be ductwork that maybe has sound breaking out of it. They could be people or any combination of the above. The path for noise is also quite variable depending on the application and the space. Often the path for noise in a commercial building is the ductwork, the supply or return or diffusers or grills within a space, but it can be the construction of the building itself, the walls, the ceilings, the roof deck, the floor. Sound will transmit through the path of least resistance in a lot of ways. And then finally, the receiver. This can be people, obviously, within a space, or even an outdoor space or a distance when there's things like property lines or bylaws that need to be met at certain hours of the day. In general, we break problems down into these 3 main aspects. When we're looking at the acoustics of a space or seeing if something is appropriate or not, we try and break things down into these 3 aspects: the source, the path, and the receiver. The source is typically, like I described earlier, the sound power, the thing that's creating the noise, often independent of environment, which would be things like air handlers or chillers or terminal units, something with a noise source contained in it. The path is a variety of different things. It could be the ductwork or ceilings or walls, or even an open or exposed area. If you have a piece of equipment that's just open, either inside or outside of a building, the path might be quite obvious, just a distance to the receiver. And then finally, the receiver, as I mentioned earlier, typically dependent on the environment, sound pressure, which would be things like a classroom or a conference room, or even just a distance away from the given source. This slide does a good job of showing that this can get quite complicated because usually you don't have a single source and a single path and a single receiver. Things like a commercial building and maybe a cross-sectional view of said building would have multiple paths where sound is going to transmit through the ductwork, through the floor, through the ceiling, and then through all the openings like supply or return grills. And there's often many different ways that sound can be transmitted and can be seen. They can be a little bit complicated to understand and maybe model or diagnose. Sources, again, can be quite varied. Often these are mechanical devices that the manufacturer of this equipment would have the relevant sound power information required to understand how loud it is. There's many different types of components and machinery available, obviously, not just in the HVAC world, but in any sort of commercial or industrial application. And this slide sort of breaks down what I spoke on earlier into more component-based spectrums. So we learned earlier sound power, sound pressure, low frequency, high frequency, rumble, hiss, and this kind of ties some of that together in that things like fans or pumps or terminal units have predominantly a lower frequency spectrum of where they would operate. Things like dampers or diffusers are typically more in the mid to higher range frequency, and they would audibly sound more like a hiss type noise. If you have air moving out of a diffuser or a grill, you can sort of understand that that would typically be in a higher frequency range, not something like 63 or 125 hertz. And this can be helpful when looking at designing a space or diagnosing maybe a sound within a space. Ductwork itself often has different potentials of absorption and sound transmission. There's many different types of ductwork that's used, obviously, to transmit air and heat and cooling. But in general, flexible or fiberglass duct can have a better absorption potential than a sheet metal duct. And as you move through sheet metal duct from a rectangular to an oval to a round sheet metal duct will transmit sound quite easily without having it break out or break through or be absorbed into the material itself. We often look at things like ductwork and silencers or sound attenuators as well. And looking at a comparison of the absorption or attenuation potential, this table is kind of interesting to see the differences on where sound can be absorbed and attenuated using different elements. And this is taken from some references through ASHRAE and through manufacturers' handbooks. But in general, looking at ductwork, a 24-inch by 24-inch piece of ductwork, 10-foot long without any lining, would have minimal sound absorption or attenuation or insertion loss. So very little reduction in sound by having unlined ductwork. As you add something like a duct liner, you typically see a higher level of sound absorption, and a 1-inch liner versus a 2-inch liner yields even further benefit. Silencers typically have acoustic media contained within them to help absorb that sound energy present within a ducted system. As sound transmits through a silencer, that sound energy is converted and absorbed in the baffles to reduce the transmission of sound through it. And you can see a silencer can have quite high insertion loss values at maybe a lower length. A 3-foot or a 5-foot silencer can absorb and attenuate quite broadband attenuation in all frequencies. Silencers in general look something like these here, where there's a variety of different types and styles, and they're primarily used for attenuating ducted noise. It doesn't always have to be ducted. Sometimes they're used in unducted applications, but primarily a duct silencer is installed into an HVAC system to attenuate that supply or return sound energy. Rectangular silencers typically look something like this here, where there's an outer casing and then internal baffles that are primarily used for absorbing and attenuating that sound energy present. Another style of silencer is an elbow silencer. Elbow silencers have typically a 90-degree turn within them, where that sound energy can now be absorbed within the baffles, but the air can also be turned in that same element. To give you an example of an elbow in a practical application would be something like this here, where maybe there is not space to use a traditional straight through or rectangular silencer. An elbow silencer could work well for that purpose, where it's now dropping down through the roof deck and then turning 90 degrees throughout the rest of the duct system. Circular silencers or round duct silencers, very similar in design and intention, where sound energy would be passing through the silencer and absorbed in that outer casing acoustic media. Typically, these silencers have perforated metal on the interior, as you can see in the rendering here, and the sound energy is absorbed into that acoustic media behind the perforated metal. A couple other examples in a practical sort of picture, and you can see available in a wide variety of sizes and diameters to suit the needs of whatever application is necessary. Silencers will often also have different types of acoustic medias and media protections depending on the installed area and application. Things like polymer film lining, where the acoustic media is actually encapsulated with a thin polymer film, and this can help provide a contaminant-free environment or prevent any sort of exposed acoustic media within the airstream. And it can be used in a variety of different applications wherever necessary. Another example of a unique silencer that you may not be familiar with is a packless silencer, or these are also called reactive silencers. And these are a bit different in that they're typically completely made of metal. There's no acoustic media or material within the baffles. Rather, it's fabricated using tuned chambers that sound energy will propagate through and enter into these baffles and bounce around and be attenuated without transmitting through it as it would an empty duct type application. They can work very well for that intention, having tuned chambers to attenuate sound energy, and used a lot in applications with corrosion concerns or that need to be cleanable, or air quality standards require no absorptive material within them. The location of silencers is also something to consider, and silencers are often installed as close to the source as possible while still allowing for appropriate inlet and outlet conditions. And what I mean by that is that when a silencer is installed in close proximity to an air moving device, there can be things that need to be considered, like system effects. If it's very close to a fan or an air handler or a terminal unit, the overall operation of these devices you need to make sure that they're going to work accordingly. You don't want to cause system disruptions or increased pressure drop by maybe improperly locating something within a system. Attenuating the noise as close to the source as possible is also advisable because it prevents further transmission of that noise throughout the facility or the area in which you're concerned with. In general, when testing silencers, there's a wide variety of noise control tests and procedures that are followed, and these are typically done for measuring what we call dynamic insertion loss. And I'll take a minute to walk through the test standard and the way the test is primarily conducted to give you maybe a better understanding of how this is obtained. In general, silencers are tested for, like I mentioned, dynamic insertion loss and pressure drop under laboratory conditions. And the way it's done is that, as shown here in this image, silencers are tested in a ducted configuration under a wide variety of configurations and sizes. The test method, comprised of a sound source, ductwork, and a reverberation room, are done in accordance with an ASTM standard, ASTM E477 standard. And the way that the test is primarily conducted is that sound energy is created in the sound source and ducted and transmitted and then recorded and measured in the reverberation chamber. A silencer is then inserted into that system, and the test is redone under equivalent ideal conditions. The difference between the silenced and unsilenced measurements that are recorded and taken is the insertion loss. effectively, the higher the insertion loss, the more sound is being taken out of that system by the silencer. So it's a relatively easy standard, but I hope that gives you some clear understanding of how it's set up and why we do that test to determine dynamic insertion loss. And we call it dynamic because it's done under airflow. There's air flowing through here as well as sound, and it's measured at different duct velocities, different duct cross-sectional areas to obtain catalog data for dynamic insertion loss. Another type of consideration is radiated sound and radiated sound energy. Radiated noise is sound transmitting through a medium, typically the air, that is unducted and just moving directly from the source through whatever partition is present to the receiver. And this can often cause issues, whether it's in an open plenum above an occupied space or in an adjacent space transmitting freely through a wall or through a partition. These are often described and looked at through noise absorbing materials and noise blocking materials. And we use criteria and terminology like STC or NRC to define the effectiveness of this. STC, or sound transmission class, will often look at a product or a material's ability to block sound, whereas NRC measures and qualifies a material's ability to absorb sound. The higher the sound absorption properties, the higher the NRC. Likewise, the higher the sound blocking properties or transmission loss, the higher the STC. Acoustic panels are another type of noise control product that work very well for blocking and absorbing sound energy. Silencers and sound attenuators work great for ducted applications, but acoustic panels are highly customizable for usage around things like radiated noise concerns, where you have maybe indoor or outdoor noise sources radiating into the environment or into another occupied space. An example of acoustic panels is something like this here, a traditional barrier wall of sorts that would be erected and installed around a noisy equipment, preventing direct line of sight to that equipment and blocking that noise radiating into the environment can greatly help with the overall reduction of sound energy. Another common noise transmission path that is untreated and problematic is what we call air transfer noise, which is noise transferring from either above an occupied space or beside an occupied space. And there's many different ways of mitigating or controlling this through building design considerations like the return air openings within a ceiling, but also air transfer products like a sound boot or air transfer silencer, like a return air silencer, can work very well for this. When you look at a commercial building, and I'm not sure if you can see in my screen, but above my head, there's a return grill. These are often weak links acoustically within a building design. People will go to great lengths and specify and install high-performing acoustical ceiling tiles, but when there's a large return air grill opening within that ceiling, it lessens the overall ceiling effectiveness, or ceiling attenuation class, we also call it. And by installing a return air silencer, such as shown here, above or in conjunction with a return grill, can help mitigate that problem, where your weak link within your ceiling has now been addressed and maybe controlled. An example like this here, you can sort of see how sound energy can freely transmit through and across and into return air grills. This canopy above one of those openings can help block and mitigate that common issue. Acoustic louvers are another type of noise control product that can work very well for mitigating sound transmission. Louvers in general are a great way to ventilate a mechanical space where sound and air can sort of transmit through these louvered blades. But acoustic louvers will typically have acoustic material within the blades and perforated metal to help absorb and block that transmission of sound. An example of an acoustic louver application is this here, where you can actually see a large sort of custom solution around an actual application that helps block the visibility of the mechanical device behind it, but also prevents the transmission of sound into the environment. This was kind of a neat project I was involved with a number of years ago. It's actually on the rooftop of a heritage building that had new HVAC systems installed, and they didn't want sort of direct visibility of these shiny new galvanized pieces of equipment. They wanted a color matched sort of solution to conceal, but also acoustically prevent sound transmission of that. And it's a neat application on an acoustic louver solution. The final section I wanted to touch on today is what I'm calling quiet HVAC systems. And there's a wide variety of materials and devices and products available in the industry. And I just thought I'd take a few minutes to kind of touch on a couple of them. The four main things I wanted to introduce are quiet terminal units, or VAV boxes, underfloor air distribution, displacement ventilation, and hydronic systems. And these are all quite common in commercial buildings and something that we see a lot of usage in today's industry, but maybe lesser known to some people than others. And I just wanted to take a few minutes to explain what they are and why they might be appropriate. Quiet terminal units are something that myself and a lot of my team members here at Price have spent a lot of time on, but something that essentially integrates two products together: a traditional VAV box and a noise control sound attenuator or silencer. And the reason for it really is to create a quiet air moving device, taking a terminal unit and integrating a silencer into its design. And I mentioned here, it's great for sound sensitive spaces that might have low criteria that need to be achieved. In general, I didn't really introduce this earlier, but terminology for silencers versus attenuators can vary quite a bit. But in general, a silencer or a duct silencer is more of a traditional sound attenuating device that has baffles within it, where you have perforated metal nosing and baffles within a casing. This is what we refer to as a silencer. Whereas an attenuator is more of a line duct application. And in general, just to define it fully, an attenuator is more of a line duct section that would have acoustic material applied to the outer surfaces. And these are typically either 3 or 5 feet in length. Whereas a silencer is also typically 3 or 5 foot in length. And they have these internal acoustic baffles with acoustic media in that baffle. These often also have the option for a media protection, like I mentioned earlier, a polymer film lining or a fiberglass cloth lining to help prevent any sort of exposure of that media to the airstream. And the reason for this type of development and solution is that terminal units and silencers are tested to two very different standards. In general, terminal units are tested to an ASHRAE 130 standard for airflow and sound, whereas silencers are tested to a different ASTM E477 standard. And I mentioned and showed in quite good detail the ASTM standard for silencers earlier. What happens is that when a silencer tested in that configuration for ASTM E477 is close coupled to a terminal unit, the overall results can be what we call unpredictable. And I want to take a minute to explain why that is. Well, in general, when you have a terminal unit, there's typically discharge sound power associated with it. Depending on the airflow and the static pressure and the size of terminal, there'll be the corresponding sound power associated with it. From that sound power, we typically deduct the silencer's insertion loss. Like I mentioned earlier, this would be a straight deduction. And by doing that, you can see the formula here would effectively yield a predicted value of a very quiet discharge sound level, approximately NC24. The problem with this prediction is that through testing and development, we've found this isn't typically the case. Taking a silencer and a terminal unit that weren't intended to be close coupled together can result in higher overall discharge sound levels, not the ideal predicted levels. And really the reason for this is that the ASTM standard I introduced earlier has equivalent empty duct diameters upstream and downstream of that silencer. It's tested under almost ideal conditions without any real system effect applied to it as part of the standard. When a silencer is close coupled with a terminal unit, the terminal inlet condition is now applied, and that's what you see in practical reality, is that the damper positioning of the terminal and the close proximity can increase that discharge sound level. And because of that, this is where a quiet terminal unit with an appropriately selected and designed integral silencer really helps the situation. This device now is tested as an assembly to the appropriate ASHRAE 130 standard and can yield very low discharge sound levels, where it's now not two differing products tested to two differing standards. It's tested as a unique assembly to the appropriate standard, and it works very well for quiet air moving devices. Another type of HVAC system I wanted to mention with respect to quiet nature is displacement ventilation. Displacement ventilation is a little bit different from a traditional mixing overhead VAV system in that air is typically introduced at lower velocities closer to the occupant, and because of that, it can have a number of benefits. For one, it can improve the overall air quality of a space, but it also has very low discharge sound levels because of the velocity and the temperature of air being introduced in this manner. And you can see on the image here, comparing a mixing ventilation system with an overhead supply and return system compared to that of a displacement diffuser, lower, closer to the occupants within the space. A couple actual examples of displacement ventilation are shown here, where there's typically diffusers or displacement ventilation diffusers installed closer to the occupants, and air is introduced at very low velocities at a comfortable rate into that area, conditioning a space without maybe the noise that might be present in a traditional VAV system. You can see highlighted there. Another system that can often have low sound criteria is hydronic systems. Chilled beams or radiant panels that have the power of water being used in conjunction with lower velocities and volumes of air can help create a quiet space as well. And a couple examples here of chilled beam, whether it's a modular or a linear type beam system, can have extremely low background sound requirements associated with them as well. In summary, we went through a lot of material here in the last 50 minutes or so, and I hope you found this informative, talking a lot about some of the fundamentals and the background of sound and acoustics, the importance of sound. We reviewed a lot of the relevant terminology, the sound power, sound pressure, my fire analogy, which I hope stays with you for years to come, and all of the relevant terminology on frequency and NC and RC. We reviewed the three main aspects again: source, path, receiver, what those are and why they're important to understand and maybe even use for diagnosis purposes. And then finally left off with a quick introduction of some quiet HVAC systems, such as the quiet terminal units with that integral silencer. I did have some time, I believe, for questions. If anyone has questions, please feel free to ask. We can use the chat, or you're welcome to unmute yourself. I also have an email address I'll leave you guys with if you want to reach out. If you don't have time to stay on, by all means, send me an email, my team an email. We'd be happy to talk with you offline.
Yeah, awesome. Thanks so much, Chris. We do have one in the chat. And again, feel free, everybody, to pop something into the chat if you have something. This comes from Urton. Open ceiling design with fan power terminal units is very common in Seattle, using NC values calculated based on AHRAE 880 and 885. standard is always tricky due to the attenuation values. Could you elaborate on the limitations of using NC or importance of understanding the environment, building material, etc.?
Great question. So this is quite a common thing that, a lot of more modern traditional building designs are moving to this exposed ceiling, lack of a block between the actual air moving devices and the occupants within it. There is some standard deductions that are commonly used for ASHRAE 880 or 885, and I do agree that this can be limiting and not maybe the most representative way to actually analyze how loud a sound or a device will be within that space. What we primarily do in this example is rather than using some of the common deductions and standard ways that ASHRAE references, performing more of an acoustic analysis where you would take the raw sound power data from that device and look at sound transmission and sound propagation into a space to understand how it might be perceived. So it's a little bit more complicated than maybe just taking a manufacturer's sound data directly out of the catalog and applying it with that corresponding NC. And like you mentioned, it can be a limitation of using that. Whereas terminal units and fan coils and fan powered boxes will often have an NC associated with them. They're often using those standardized ASHRAE deductions, which might not be the best way to do it.
Awesome. And then what about, what are your thoughts about sound canceling systems?
Yeah, so this is, again, another technology that's been used for many years and something that we're seeing benefit for, sound masking or even sound canceling. There's a world that I didn't touch on today called active noise control. And the technology is advancing every year on this stuff where the primary basis is that it's actually taking a measurement of the sound and producing the opposite frequency of what that would be to sort of cancel out what is audibly heard. Some automotive manufacturers are even using this in their trucks and vehicles, that when you're driving down the highway, it's going to produce the opposite spectrum of sound to cancel out what you're audibly hearing. So personally, I think there's a space for it in the industry, and I think people are using it in whether it's an open plan office or a private office to help the overall acoustics within that space. So I personally don't know a ton about it. It's quite new and it's changing, but it's I think something that can be helpful.
Awesome, thank you. Everybody, we've got about 5 more minutes. And as Chris said, he's got his email there below, and is happy to kind of answer some emails off. So it's very gracious of him. Again, everybody appreciate your time and want to be respectful as well. So if you would like to head off, that is a good stopping point there. And then otherwise, we'll stay on for a couple more minutes and answer questions. If you have any ideas on topics or things that you want to hear about in the future, please feel free to reach out. We would love to hear anything from the field, and always try to take those into consideration when making these plans and presentations.
One other thing I'll just mention, Ty, I didn't get into it in today's presentation, but we do have an acoustic analysis software that we've developed at Price. And if anyone's interested in it, it does a lot of what I went through today in today's presentation, taking the source path receiver concept into more of a modeling situation. And by all means, send us an email if you're interested in seeing it or utilizing it in your professional careers. And we'd be happy to kind of hook you up with it and give you a license for it.
All right. I think that is good. Chris, thanks again. And appreciate everybody in their time.
Thanks, everyone. Appreciate your time as well. Have a great rest of the day.